Hi and welcome to this video about hooking functions. In this video we'll take a look at how to hook functions in a very simple way, and we'll extend on that in the next video. So what does hooking mean here? When we want to hook functions, it means we'd like to intercept their execution, which means we want to look at the parameters of the function. We might want to call the original function or not. We can change parameters. We can do something before and or after the function is called. Really, we have full control over the function if it is properly hooked. And there are two techniques that are commonly used for hooking functions. The first one is to patch the input address table. So we can do that just once. We just need to do that once, and the function that's going to be patched there is going to be our hook function. This is definitely possible to do. The other way is what's usually referred to as inline hooking, which means replacing the beginning of the function with some jump instruction somewhere where our hook function is going to be located at, and then we can of course save the original function address and maybe call the original function or not based on what we'd like to do. So inline hooking is usually more powerful because it means that even if someone calls getProcAddress to get dynamically the address of the function, it's still going to be hooked. Whereas with the IAT, if you patch the input address table, it only works when functions are being called statically. That is, they're being called by the code that's already being compiled. If someone calls getProcAddress, someone will be able to bypass the IAT hook. So I'm going to work with inline hooking in this example. So let's see how we can do that. Obviously, we don't want to write everything from scratch. We'd like to use existing libraries. There are a few of those that we can use that will do the work for us. I'm going to use one called Detours, which is a Microsoft library, but there are others which are at least equally good. So I'm going to work with this application that we've seen at some past video. This application just draws this nice ellipse here that's being resized based on the size of the window. This is just an example, of course. I'd like to hook some functions within this application. The hooking we're going to be doing are going to be locally in our process. In the next video, I'll show how to hook functions in a different process, which is a bit more difficult. So I'd like to keep it simple for this first video by doing hooking in our own process. So I want to use the Detours library. Where can I get it? Well, you can get it with VCPackage if you're using that. In fact, I am, but I'm going to make this project self-contained by getting Detours from NuGet. So I'm going to right-click References here and use Manage NuGet Packages. Then I'm going to browse here and look for Detours. If you look for Detours, you'll find this entry here, Detours by Microsoft. I'm going to install that. So I'm installing that. There's a little dialog that we have to accept, and it is in. So once it's part of our project here, we can go ahead and include the detours.h header that would allow us access to the Detours API. And what I want to do here is to add a function here called install hooks. That's going to install the hooks that we're going to use. Just a simple function I'm going to write right here. I'm not going to even bother returning any success or error, just going to do the deed. If anything goes wrong, we'll figure it out with the debugger and we'll fix it. So it really depends on the API we need to use. In this particular case, I'm using the Detours library. It has a certain API, which of course is documented. Here's the basics of that. The first thing we need to do is call Detours begin transaction. So the idea here is that the way to work with Detours is by starting a transaction. That transaction is going to encapsulate our changes while actually transaction begin. And then we'll do the changes we'd like to do, and then we'll just commit the transaction. That's the basic idea here. So we have Detours transaction begin. Technically, we need to look at the return values here, but I'm going to dispense with that here. We'll see if everything goes according as planned. We'll see. So here's the commit part, and now we just have to perform detour attach. This is one of the options to attach or to hook really a function. And we're going to get back the pointer to the original function, which of course is very important, so we can call the original function and we don't lose any functionality. So first we need to do some preparations. We have to have a variable that contains the original function, and also we have to have the replacement function. So as my first example, let's hook the ellipse function so it does something perhaps different. So first we need a variable to hold on to the original ellipse. So I'm going to use a declaration specifier here. This is actually not declaration specifier, but decl type from C++ 11. So we have the function ellipse. This is what I'm interested in a pointer to that. So let's have a pointer. This is just so I don't have to explicitly specify the type as a function pointer, which is really gory, and with pure C would have to do that, but with C++ 11 and later we can get away with that by letting the compiler infer the type automatically, because the compiler knows what the ellipse function is and what that looks like. Let's call that orig ellipse. That's going to be the original ellipse. And we're going to initialize that to the ellipse function. So we have the pointer there already kind of ready to go, but it's going to be looked up by the detours attached. So we need to pass here the address of orig ellipse. So that's the variable we have here, and need to cast that to avoid pointer, so the compiler is happy. This is how the detour attach function requires it. And then the second parameter is our detour, that is our hook function. So let's create it. So our hook function has to have the same prototype, of course, as the original function. Let's call that hook ellipse. And if you look at the documentation, you'll find that ellipse has 4 parameters, actually 5 parameters. We have the device context, and we have x and y of one corner of the imaginary rectangle where the ellipse is going to be drawn, and then the second set of coordinates. That's going to be our function. It should return a boolean. Of course, as I mentioned, we can always verify by going to the documentation, doing something like ellipse. We can see that the ellipse function, well, actually not this one, that's the ellipse function I'm looking at. This is the one. You can see it has these 5 parameters and returns a boolean. So I need to make sure that I keep this correct. And now I can pass here my hook ellipse function. And that is basically it. If I just do that and I go ahead and just return true here, let's see what happens. I'm going to build that. Let me build the x64 version. I don't really like a 32-bit version, although that would work as well. And if I press Ctrl F5, here's what I get. I get nothing, and that's because we've essentially disabled the ellipse function because we're not calling the original. So nothing is happening here. So at the very least, I probably want to call the original ellipse function. Let's do that to make sure that indeed our functionality is not destroyed. So I'm going to do that and run this again. And now we can see the ellipse is back, mightier than ever, but obviously this is not very useful because we're not doing anything special here, but the function is hooked. And we can of course put a breakpoint here to see exactly when this function is being called, which might be interesting. In this particular example, it might not be that interesting, but perhaps expected. You can see it's coming from our window procedure where we call the ellipse functions ourselves. But of course, it would hook the ellipse function coming from any kind of code in my process. Could be from some other component or some control that uses the ellipse API. Whatever is calling ellipse, we're going to intercept it. That's the power of hooking. So this is coming from this function, which of course makes sense. So now we can see the ellipse, but if I move the window, things like that gets resized again, we get a call, and this becomes pretty annoying. So if I continue with that, we have the window. Great. What can we do with that? Well, we can do anything we want really. First, we can log the call to the ellipse. Let me do something very simple here. I'm going to add and include for ATL base. So ATL is the active template library, which I'm not going to actually use in practice here, but it does have a very convenient ATL trace macro that accepts stuff related to formatting of text very easily. I could also use std format from C++20, but I'm not going to go down that route here. So let's say ellipse called, and we can specify here, let's say %d, %d, and then %d and %d again. I'm going to just dump the parameters for the coordinates. like so. So ATL trace will dump that to the debugger if the debugger is running, or to another tool that can capture that, which we'll see in the next video. So I'm going to press F5, and now we have our ellipse here. Let's go ahead and find the output here. So let's find the output. Microsoft change here the text to icons, so it's not very easy to find out where is actually the output. So here's the output. You notice that the ellipse was called, in fact, multiple times. If I go ahead and bring the ellipse here, let me just minimize that a little bit, but of course we had many ellipse calls happening. So you can see the coordinates are changing at the bottom because we have more text coming in. Let me just remove this to make some more room here. So you can see coordinates are actually changing and we get that trace. So something is definitely happening. And of course we can make any changes we like. For example, let's go ahead and add say 30 to x1, and same goes with y1, and change x2 to 30 less than it was. Same goes with y2, just for fun. I'm going to press Ctrl F5 to run this without the debugger. So here's what we get. Now the ellipse doesn't span the entire window, but is 30 pixels less in all directions, you can see here. Let's do something else, again, just for fun. Let's say I would like to change the color of the bounds of the ellipse. So let's create a pen here. Let's have a pen here. Let's call the function createPen and create a little pen here. I'm not saying it's going to be the most performant or efficient way of doing that, but good enough for our purposes for this demonstration. I'm going to create a red pen, which is a 3, let's say, why 3? Let's grab something else, like 6 pixels wide. And we'll use that pen by calling the select object API, telling the device context, here's a new pen for you, please use that, and give me back the old pen. So we're going to call the original ellipse function so that the ellipse is actually drawn. And then we need to clean up, which means selecting the old pen, so we don't get into some weird state, and also not to leak the object. We're going to delete the pen that we created. Of course, we could have just created that once as a static variable, for example, or global, but this simple example is good enough. So now, every time someone draws an ellipse, the bounds of the ellipse are going to be drawn like this, with a 6 pixel wide red pen. That's what I decided to do here. So in fact, you can do anything you want, you get the idea. So you might be thinking, maybe that's kind of useless here to hook the ellipse function, because we're calling the ellipse function here directly, and maybe that's not so smart, because we can just change the ellipse here to anything we want. So remember that it also works for any ellipse call in this process, regardless of whether we are actually calling this function or not. Just to prove it, let's do something a bit more interesting. Let's hook another API called heapalloc. The heapalloc API is going to be called, might be called perhaps, by multiple components within the process, because heapalloc is also the one called by the malloc function, could be, or the new C++ operator. So let's go with that. So let's add another decal type. See how easy it is to add another function to hook. So here's heapalloc, that's going to be what we need. And then we have to store the original, so we have org hook, heapalloc. And we're going to point that to the heapalloc function, the real function. And then we need to hook it, so obviously we need another function that has the same prototype as heapalloc, and we can use the documentation for that. But here's what that looks like. It returns a p-void, the pointer to the allocated memory. Let's call that hook heapalloc. It accepts 3 parameters. The first one is the handle to the heap, where this allocation is supposed to take place. Then we have a bunch of flags, and then we have the actual size. How many bytes are we supposed to allocate? So the very basic thing I'm going to do is of course call the original function, because if I don't do that, then obviously no allocation will take place and the process is likely to crash. So let's we can try that as well, but let's go ahead and just make sure that things look normal, at least from an outside perspective. So we have the hook function. The only thing left to do is to actually perform the hook by using detours attach here. So detour attach, this time we're going to grab org heap alloc, and then our hook function is hook heap alloc. And just to prove things are actually being hooked, let's put a breakpoint here in our hook heap alloc function and press F5 to run this. So notice we stopped the breakpoint fairly early. Where is that actually happening? So interestingly enough, it is coming from WinMain when we call the register class function that registers the window class with Windows. Apparently this register class calls some helper function that calls another helper function which happens to need some memory. In fact, it requires at this point 200 hex, that's 512 bytes. That's what it requires, and that's the handle to the heap, which we can do certain things with. So obviously this is in fact happening. If I press F5, continue running, we now get to another heap alloc allocation almost immediately, this time as part of the create window ex function. So create window here is actually create window ex, that's calling something called create window internal that calls this var anti-user create window ex, and then so on and so forth until someone actually needs some memory. So we can track memory allocations with this technique. This is something very simple that we can do. And we can make changes, of course. We can allocate more memory and store some metadata in that extra memory. We can do virtually anything we want. Of course, if we mess things up, things will not work as we intend. So for example, if we say do something crazy, like pass to the function size divided by 2 to the API, I actually have no idea what's going to happen, but my guess is that we're going to crash at some point because we're not going to allocate enough memory for whoever is asking. I'm pressing F5 here. Notice we have an exception here. Something here is wrong. It says access violation, which makes sense. It tried to allocate, say, 200 bytes, and then we gave the function, the caller, just 100 bytes. It would still think that it has these 200 bytes and then tried to access beyond that 100 bytes, and we get some kind of buffer overflow, but in fact the buffer could have nothing later on, and that would cause an access violation, which is a very famous code here with 00C and 00F5 there. So that's something you might have seen. And so obviously that can't work very well, and the process will crash. So we need to make sure we're not making or causing any kind of damage. But at the very least, we can hook any function that we want and do whatever we want. In the next video, we'll do something a bit more ambitious. We'll try to hook a function in a different process, maybe trying to hook a function in Task Manager that would allow us to, say, hide processes. That's going to be our next video.